It's okay?
That's right.
Okay.
So, ladies and gentlemen, my name is Bartłomiej Walczak. I'm working in R&D department at Solaris Bus and Coach. I'm a PhD student at AGH University of Science and Technology in Poland. Today I'm going to speak about the measurements of load acting on electric bus in urban traffic, which I prepared together with my colleagues Piotr, Malaca, Dariusz, Michalak, and Wiesław, Staszewski. First of all, aim and plan of the activities. In the bus industry, there are no generally available guidelines regarding fatigue calculation, for example, analogous to DIN EN 12663 from the railway industry, and the manufacturer must rely on his experience in selecting the appropriate loads for strength analysis. The aim of activities are the measurements of load acting on the electric bus in normal operation, which will help to improve the design process and allow safe optimization using state-of-the-art tools. To meet that goal, in the first step, pre-test finite element method simulation of the prototype structure was done, and key points of measurement were selected. Then the bus was instrumented and measurements of standard maneuvers and driving through obstacles were done. In the third step, test drives in urban area were measured. After this step, data was analyzed and sections with the highest influence of fatigue damage were selected. These sections were scanned for further numerical analysis. So the gathered data in the future will be used for the following works. First of all, definition of extreme load conditions, defining the fatigue cycles. Scanned roads will be used for advanced dynamic numerical analysis, and reference signals will be used for validation of numerical models. Now a few words about the measurement object. They were done on prototype bus visible on the above picture. It's almost 15-meter long 3-axle bus with traction motor power of 300 kilowatts and more than 620 kilowatt-hour of energy stored in the batteries. Gross vehicle weight is 26 tons, which assumes up to 65 seats and more than 100 passengers in total. On this slide, you can see why the electric bus is different than the diesel. So the main reason are the mass parameters of the elements assembled on the roof. In the standard diesel bus, only air conditioning unit is assembled on the roof, but in case of electric bus, total mass of roof elements exceeds 3 tons, including 3 traction batteries with cooling system, traction, electronics, pantograph, and braking resistor. In the lower part of the bus, additional 4 traction batteries with the weight of 2,400 kilograms are present. And finally, traction motors, which weight is only 260 kilograms, which seems to be low weight in comparison to diesel bus. It all gave us more than 5 tons of the powertrain elements. In the first step of the measurements of our works, finite element method analysis was done using SimCenter Nastran software. There were 4 made load cases of generic loads used as a pretest. It was emergency braking, cornering, driving through bump, and frame twists. On above picture, you can see stress envelope of that load cases, which the most loaded areas were chosen. As you can see in the table 3, it was chassis, a right wall, and the roof. Selected points for measurements. As you can see on exploded view of the structure, on the left side, there were assembled strain gauges. Most of them were located in the chassis. It was 21 measurement points, where the highest loads from the suspension of the powertrain and the powertrain arm are introduced. Sidewalls were investigated mainly in the door areas, and it was 7 points, and roof below the traction batteries, there were 2 tensometric points. Also, suspension components were instrumented, and there were 13 tensometric points located on the steering rod, stabilizers, and reaction rods. Additionally, there were 5 accelerometers on sprung mass, and the main goal of location give me a second, the accelerometer here is the collection of the accelerations of the body frame, which will be used in the further analysis to prepare fatigue assessment similar to DIN EN 12663 from railway industry. Others are used for observation of the local responses of the structure. Also on each wheel hub, accelerometers was assembled, which signal in the future can be used for dynamic FE analysis. As a validation signals, we used also wire linear displacement sensor, which were located near each air spring, and also in 3 sections of the structure where we measured the diagonals displacement. All the tests were recorded by camera located in the windshield, and also signals of powertrain and tachograph were recorded via Canon network. First testing phase assumed scenarios like emergency braking, slalom, bump, bad quality road, railway crossing, and crossing the car. So the most loading for chassis were emergency braking and slalom. The highest registered forces in the suspension elements were registered for that 2 tests. What is shown on picture 7, we can see that there was extremely high force in the rods of the driving axle. And also bump test was causing highest response of the roof elements and sidewalls. In the highest part of the picture 7, you can see maximum magnitude of acceleration in loading direction. For braking, it was 6.6 meters per second square of deceleration. For slalom, the highest magnitude was -4 meters per second square in the y-axis. Together with local transportation company from Poznań, 3 city roads of varying difficulty were chosen. Together, it contains 79 sections of different quality of roads. Bus was tested in 2 configurations. First included only sitting passengers, and second fully loaded. And for the purpose of simplified fatigue analysis, as I mentioned, analogous to the one from the rail industry, acceleration sensor from bus interior was analyzed. To extract cycles such as braking and cornering, signal was filtered in the Butterworth filter for longitudinal and lateral axis, and it was reduced to 10, the boundary was 10 Hertz. For vertical axis, it was 20 Hertz. After that, it was processed with the rainflow counting algorithm, which extracted cycles. So for the purpose of fatigue simulation, this data need to be extrapolated for equivalent of 1 million kilometers. In the next step, influence of each road on fatigue strength was checked. For this purpose, based on strain gauge result, each strain gauge was processed with rainflow counting, and the accumulated damage was calculated using parallelogram minor law. On picture 10, you can see the results for representative bus areas, and road sections connected with the highest accumulated damage for each superstructure area was selected for scanning.
I'm sorry, may I recall you about time, okay?
Okay, in the last step, selected roads were scanned using high accuracy kinematic LiDAR. Total length of scanned sections was about 10 kilometers. You can see here the scanned sections and conclusions. The measurements are to be the basis for more accurate strength analysis, which may allow responsible vehicle weight optimization. Data from the bus body acceleration are to be used for preparing the basic fatigue load cases. Scanned roads used with state-of-art software, nonlinear characteristics of the suspension and advanced tire model gives opportunity of realistic drive simulations. Further work will focus on numerical analysis and correlation with the test results. Also, a classification of scanned road qualities and its deeper analysis will be done. Thank you very much for attention.